The search for the most extreme environment in the known universe begins with a problem of definition. Astronomers do not describe violence in emotional terms. They measure it. They measure how much energy is released, how fast matter moves, how hot gas becomes, how quickly stars are born and destroyed, and how long such conditions can persist without collapsing into equilibrium. By these standards, many objects compete for attention: exploding stars, neutron-star collisions, gamma-ray bursts, and quasars powered by supermassive black holes. Yet when researchers began assembling data from some of the most powerful observatories ever built, one location repeatedly refused to fit within existing limits. That location is known as Phoenix A. If you're ready to explore the most extreme forces in the universe, Phoenix A is calling. Subscribe now and witness power, speed, and heat that challenge everything we know about space. Phoenix A lies far beyond the Milky Way, at a distance of approximately 5.7 billion light-years from Earth. Its light began travelling toward us when multicellular life on Earth had not yet appeared. In astronomical terms, Phoenix A is observed at a redshift of about 0.596, placing it in an era when the universe was roughly 2/3 of its current age. This distance alone makes detailed study difficult, yet Phoenix A stands out so strongly that it cannot be ignored. It announces its presence through extraordinary radiation output, extreme temperatures, and physical processes occurring at rates rarely observed anywhere else. The story of Phoenix A entered modern astronomy in the early 2010 seconds during large X-ray surveys of the sky conducted by NASA's Chandra X-ray Observatory and the European Space Agency's XMM-Newton telescope. These missions were designed to detect hot gas in galaxy clusters, structures so massive that they bend space, trap millions of light-years of plasma, and contain hundreds or even thousands of galaxies. Most clusters emit X-rays steadily and predictably. Phoenix A did not. Its X-ray brightness was so intense that it immediately signaled something unusual at its core. Follow-up observations revealed that Phoenix A is not a single object, but the central galaxy of an enormous galaxy cluster, now known as the Phoenix Cluster, catalogued as SPTCLJ234444243. The cluster itself contains a mass estimated at more than 2 quadrillion times the mass of the Sun, making it one of the most massive gravitationally bound structures ever observed. But mass alone does not explain violence. Many clusters are massive. Phoenix A is different because of how energy flows through it. At the heart of the Phoenix cluster, vast amounts of gas are heated to tens of millions of degrees. Under normal conditions, such gas should cool slowly over billions of years, radiating energy and settling into a stable state. In most clusters, this process is regulated by the central supermassive black hole, which releases energy through jets and radiation that reheats the gas, preventing runaway collapse. This self-regulating balance, known as feedback, is one of the cornerstones of modern astrophysics. Phoenix A appears to be breaking that balance. The initial clue came from X-ray measurements, indicating an enormous rate of energy loss from the cluster's core. Estimates showed that hundreds of billions of solar luminosities were being radiated away in X-rays alone. This suggested that gas was cooling far faster than expected. At the same time, infrared observations from the Hubble Space Observatory and optical data from the Hubble Space Telescope showed intense activity in the central galaxy. These independent signals pointed toward a system operating far outside the norms established by decades of cluster research. To understand why Phoenix A matters, it helps to consider scale. The Milky Way forms roughly 1 to 2 stars per year. Phoenix A's central galaxy forms hundreds of stars every year, possibly exceeding 1,000 at its peak. This is not a brief burst lasting a few million years, but a sustained process inferred from multiple wavelengths. Such activity requires enormous reservoirs of cold gas, yet Phoenix A sits inside one of the hottest environments known. Reconciling these facts became one of the central challenges driving further investigation. The designation of Phoenix A as a candidate for the most violent known environment does not rest on a single record. It rests on the simultaneous presence of multiple extremes. Gas temperatures exceeding 80 million degrees coexist with cold molecular clouds. Powerful relativistic jets punch through intergalactic space while gas continues to fall inward. Shock fronts ripple through the cluster, while stars form at rates typically seen only in the early universe. Each of these processes alone would be noteworthy. Together, they suggest a system where regulation has failed and energy is being redistributed on enormous scales. Astronomers quickly realized that Phoenix A offered more than a curiosity. It offered a laboratory. Because the light from Phoenix A has traveled billions of years to reach Earth, it allows scientists to study cluster behavior at a time when the universe was more active and chaotic. At the same time, the level of detail available from modern instruments allows precise measurements of temperature, density, velocity, and composition. Few systems combine distance, extremity, and observability in this way. The instruments involved in this investigation form a global network. Chandra provided high-resolution X-ray images revealing cavities and temperature gradients. XMM-Newton contributed spectroscopy capable of identifying the chemical elements present in the hot gas. The Atacama Large Millimeter or Submillimeter Array detected cold molecular gas despite the surrounding heat. The Hubble Space Telescope resolved the structure of the central galaxy, while ground-based observatories measured motion and mass through gravitational effects. Each dataset reinforced the same conclusion: Phoenix A is not behaving like a normal galaxy cluster. What elevates Phoenix A from unusual to exceptional is the persistence of its activity. Many extreme events in the universe are brief. Supernova explosions fade within months. Gamma-ray bursts last seconds. Even the brightest quasars flicker over tens of millions of years. Phoenix A appears to have sustained extreme conditions over hundreds of millions of years. This longevity amplifies its impact, allowing violent processes to reshape the cluster environment repeatedly rather than in isolated bursts. The question driving this journey is not whether Phoenix A is violent, but why. Why does cooling proceed so efficiently here? Why does the central black hole fail to suppress gas collapse? Why does star formation continue despite conditions that should shut it down? These questions are not philosophical. They are empirical, rooted in observation, measurement, and physical law. Phoenix A forces astrophysicists to test assumptions embedded in simulations and models used to describe the largest structures in the universe. Studies of Phoenix A have been incorporated into broader analyses of galaxy and cluster evolution. Many models rely on feedback processes to regulate star formation and gas cooling in massive systems. Observations of Phoenix A show that, under certain physical conditions, these processes do not fully suppress cooling or star formation. These findings are used to constrain parameters in simulations that track the development of large-scale cosmic structure. Initial analysis of Phoenix A focuses on identifying the measurable properties that distinguish it from other galaxy clusters. Prior to detailed examination of jets, shock structures, dark matter distributions, or black hole activity, researchers compare its observed temperatures, luminosities, mass flows, and star formation rates with established cluster populations. These comparisons are based on thresholds derived from multi-wavelength observations using instruments designed to quantify extreme physical conditions. Ongoing observations of Phoenix A are conducted with both current and planned astronomical facilities. The system is analysed as an evolving galaxy cluster whose emitted radiation records physical conditions at the time of emission, billions of years in the past. Data from these observations are used to reconstruct temperature distributions, energy flows, and dynamical processes occurring on scales larger than individual galaxies. Inside the Phoenix galaxy cluster, reaching Phoenix A means first understanding the vast structure that surrounds it. Phoenix A does not exist in isolation. It is embedded deep within the Phoenix cluster, a gravitational system so large that its influence extends across millions of light-years. Galaxy clusters represent the largest bound structures in the universe, assembled from hundreds to thousands of galaxies, enormous reservoirs of hot gas, and an invisible framework of dark matter. What makes the Phoenix cluster remarkable is not simply its size, but how efficiently it concentrates matter and energy into its central regions. The Phoenix cluster spans roughly 7 million light-years from edge to edge. Within this volume, astronomers have identified hundreds of individual galaxies, ranging from small dwarf systems to massive ellipticals. These galaxies do not move randomly. Their velocities, measured through redshift surveys, reveal speeds of several thousand kilometers per second as they orbit the cluster's gravitational center. Such motion immediately signals an enormous underlying mass. Using these velocities alongside gravitational lensing measurements, scientists estimate the total mass of the Phoenix cluster at more than 2 × 10⁻15 solar masses, placing it among the most massive clusters ever observed. Only a small fraction of this mass is locked inside stars. Roughly 85% exists as dark matter, forming an extended halo that shapes the cluster's gravitational potential. This dark matter distribution was mapped using weak gravitational lensing, where the cluster subtly distorts the images of background galaxies. Observations from the Hubble Space Telescope and large ground-based observatories such as the Magellan telescopes in Chile allowed astronomers to reconstruct how mass is distributed across the cluster. The resulting maps show a dense central concentration, providing the gravitational anchor that holds gas and galaxies in place. The remaining visible mass is dominated not by stars, but by hot gas filling the space between galaxies. This intra-cluster medium contains more mass than all the stars in the cluster combined. In the Phoenix cluster, this gas reaches temperatures of tens of millions of degrees, hot enough to emit X-rays continuously. Chandra and XMM-Newton observations reveal that this gas is not uniform. Its density increases sharply toward the cluster center, forming a bright X-ray core that signals intense gravitational compression. Unlike gas inside galaxies, the intracluster medium is extremely thin. A cubic meter of this plasma may contain only a few hundred particles, far less dense than any vacuum achievable on Earth. Yet across millions of light-years, this sparse gas adds up to enormous mass. In the Phoenix cluster, X-ray brightness measurements indicate gas densities in the core significantly higher than those found in most clusters at similar distances. This elevated density plays a critical role in shaping the cluster's behavior, allowing energy losses to occur rapidly and setting the stage for extreme activity deeper inside. The Phoenix cluster was first identified not through visible light, but through its imprint on the cosmic microwave background. It was discovered by the South Pole Telescope during a survey that searched for distortions caused by the Sunyaev-Zeldovich effect. As hot electrons in the intracluster medium scatter background microwave photons, they leave a detectable signature that does not fade with distance. This technique allows astronomers to find massive clusters across much of cosmic history. The Phoenix cluster stood out immediately due to the strength of its signal, indicating an exceptionally deep gravitational well. Once identified, the cluster became the target of intensive follow-up campaigns. Optical spectroscopy measured galaxy velocities and confirmed cluster membership. Infrared observations detected dust and star-forming activity near the center. X-ray imaging mapped temperature and density variations in the gas. Each wavelength added a layer of information, revealing a system that was not only massive, but dynamically active. Unlike relaxed clusters, where matter settles into smooth distributions, the Phoenix cluster shows signs of ongoing motion and energy redistribution. One of the most striking features of the Phoenix cluster is the sharp contrast between its core and outer regions. Far from the center, gas temperatures and densities resemble those seen in many massive clusters. Moving inward, however, conditions change rapidly. X-ray spectra show cooling gas, pressure gradients, and structural irregularities that indicate disturbances propagating through the medium. These features suggest that the cluster is not in equilibrium, but instead undergoing continuous internal reconfiguration. Galaxy clusters grow through mergers, and evidence suggests the Phoenix cluster has experienced multiple such events. Substructures detected in galaxy distributions hint at smaller groups being absorbed over time. As these groups fall in, their gas is stripped away by ram pressure, adding to the intracluster medium and increasing its density. This steady accumulation of material feeds the cluster's central regions, reinforcing the conditions that drive extreme activity. The Phoenix cluster's mass growth rate is unusually high for its epoch. Cosmological simulations predict that clusters of this size should grow more slowly at this stage of the universe's evolution. Yet observational data suggest that Phoenix has continued to accrete matter efficiently. This rapid growth increases gravitational compression in the core, raising gas densities and accelerating energy loss through radiation. The cluster effectively funnels matter inward, delivering raw material toward its center on vast scales. Temperature maps constructed from X-ray data show that the intracluster gas does not cool evenly. Instead, cooler pockets form near the center, embedded within hotter surroundings. These temperature variations trace the movement of gas as it responds to gravity, pressure, and energy input. The presence of such gradients indicates that heat transport within the cluster is inefficient, allowing localized regions to evolve independently. This breakdown of uniformity is a key feature distinguishing Phoenix from more stable systems. Chemical analysis of the intracluster medium adds another layer of insight. X-ray spectroscopy reveals the presence of heavy elements such as iron, silicon, and oxygen. These elements were forged in stars and dispersed by supernova explosions over billions of years. In the Phoenix cluster, metal abundances are particularly high near the core, indicating a long history of stellar processing and gas recycling. This enrichment enhances the gas's ability to radiate energy, further accelerating cooling processes. The geometry of the cluster also matters. The Phoenix cluster is not perfectly spherical. Slight elongations and asymmetries suggest past interactions and directional inflows of matter. These structural features influence how gas moves and where it accumulates. Regions of higher density experience stronger cooling, while lower density zones remain hotter. Over time, this uneven evolution amplifies contrasts within the cluster, concentrating activity toward the center. Observations show that the Phoenix cluster contains a tightly coupled system of dark matter, galaxies, and intracluster gas. Dark matter establishes the gravitational potential, while galaxies trace this structure and contribute stellar mass and chemical enrichment. Hot gas fills the intracluster volume, radiating energy as it responds to gravitational compression and pressure gradients. In this system, matter is transported efficiently toward the central regions, producing elevated densities and enhanced cooling rates. The physical conditions observed in Phoenix A are directly linked to the properties of the surrounding cluster. The central galaxy resides within a deep gravitational potential shaped by the cluster's total mass, dense intracluster gas, and ongoing accretion of material. These large-scale conditions influence gas cooling, pressure, and energy flow in the cluster core, contributing to the observed activity in the central galaxy. Ongoing observations continue to refine measurements of the Phoenix cluster's size, mass distribution, gas density, and dynamical activity. The cluster exhibits values for these properties that lie at the high end of those measured for known galaxy clusters. Its gravitational structure and gas dynamics directly influence conditions in the central regions. Subsequent analysis therefore focuses on the central galaxy located at the deepest point of the cluster's gravitational potential, the central galaxy at the core. At the deepest point of the Phoenix cluster's gravitational well sits a single galaxy that dominates everything around it. This galaxy, Phoenix A, is not merely the brightest member of the cluster. It is structurally, dynamically, and energetically distinct from nearly every other central galaxy ever studied. Astronomers refer to such systems as brightest cluster galaxies, but Phoenix A stretches that category to its limits. Its physical scale, luminosity, and internal activity immediately signal that something unusual is happening at the heart of the cluster. In visible light, Phoenix A appears as a massive elliptical galaxy extending hundreds of thousands of light-years across. Its stellar halo is smooth and diffuse, the result of countless mergers over cosmic time. These mergers built a galaxy whose stellar mass is estimated to be several trillion times that of the Sun, placing it among the most massive galaxies known. Measurements from optical and near-infrared surveys show that its light profile deviates from standard models used to describe elliptical galaxies, suggesting a complex formation history shaped by repeated infall of smaller systems. Despite its large size, Phoenix A shows evidence of ongoing internal activity. High-resolution images from the Hubble Space Telescope reveal dark dust lanes across its central regions. These structures trace cold material embedded within a hotter surrounding medium, indicating the presence of gas within the galaxy rather than a purely inactive stellar population. Spectroscopic observations provide further insight into the galaxy's internal conditions. Emission lines detected in optical and ultraviolet wavelengths reveal ionized gas moving at hundreds of kilometers per second. These motions are not random. They trace organized flows toward the galaxy's center, suggesting that material is being funneled inward from the surrounding cluster environment. The presence of this gas challenges long-standing assumptions that central cluster galaxies are largely depleted of star-forming material. Infrared observations add another critical layer. Data from the Spitzer Space Telescope and later from Herschel reveal strong infrared emission associated with warm dust heated by young stars. This emission cannot be explained by old stellar populations alone. Instead, it points to ongoing star formation occurring deep within the galaxy's core. The intensity of this infrared signal places Phoenix afar above typical brightest cluster galaxies, which usually show little to no star-forming activity at similar epochs. The spatial distribution of this activity is particularly striking. Star formation in Phoenix A is concentrated within the central tens of thousands of light-years, coinciding with regions where gas densities are highest. This central concentration suggests that the galaxy is efficiently converting incoming material into new stars, rather than dispersing it. Observations with the Atacama Large Millimeter or Submillimeter Array confirm the presence of vast reservoirs of cold molecular gas, the raw material required for star formation, embedded within the galaxy's core. The mass of this molecular gas is staggering. Estimates place it at tens of billions of solar masses, comparable to or exceeding the entire molecular gas content of large spiral galaxies. This gas is not uniformly distributed. It forms clumps and filaments, some extending tens of thousands of light-years from the center. These structures trace the pathways along which material flows inward, connecting the larger cluster environment to the galaxy's central engine. Phoenix A's luminosity across multiple wavelengths reflects the cumulative effect of these processes. In optical light, it outshines nearly every other galaxy in its cluster. In infrared, it rivals starburst galaxies typically found in much younger cosmic environments. In X-rays, it contributes significantly to the cluster's already intense emission. This multi-wavelength brightness marks Phoenix A as a galaxy operating simultaneously in multiple energetic regimes. Observations indicate that Phoenix A retains significant amounts of incoming material. In many clusters, galaxies lose gas through ram pressure stripping as they move through the intra-cluster medium, and central galaxies often experience heating and turbulence that inhibit gas accumulation. In the case of Phoenix A, its position at the bottom of the cluster's gravitational potential allows cooling gas from the surrounding medium to be retained within the galaxy. The stellar populations within Phoenix A reflect this ongoing activity. Analysis of its light shows a mix of old stars formed early in the universe's history and much younger populations formed more recently. This combination is unusual for a galaxy of its type and age. It indicates that Phoenix A has not followed a simple evolutionary path, but instead has experienced repeated episodes of growth long after similar galaxies had ceased forming stars. The galaxy's central regions also exhibit strong emission from ionized hydrogen and other elements, detected through narrow-band imaging and spectroscopy. These emissions trace regions where massive, short-lived stars are forming and illuminating their surroundings. Such regions are typically associated with spiral galaxies or starburst systems, not with the largest ellipticals at the centers of massive clusters. Phoenix A, therefore, occupies a hybrid state that defies easy classification. Kinematic studies further highlight its uniqueness. Measurements of gas velocities show complex motion patterns, including inflows, outflows, and rotational components. These motions suggest that Phoenix A is not dynamically settled. Instead, it is continuously adjusting to the influx of material from the cluster. This dynamism contributes to the galaxy's ability to sustain extreme internal processes over long periods. The gravitational field of Phoenix A influences the distribution of gas and stars in its immediate surroundings, and its energetic output affects the physical state of nearby intracluster gas. Material from the surrounding cluster is transported toward the central regions of the galaxy, contributing to increased mass density and energy release on smaller spatial scales. Comparisons with other brightest cluster galaxies show that many central galaxies at similar redshifts contain little cold gas, weak infrared emission, and low star formation rates. In contrast, Phoenix A exhibits substantial cold gas reservoirs and strong infrared emission consistent with active star formation. These differences have made Phoenix A a frequent target of observational study. Observations of Phoenix A show that some central cluster galaxies can retain gas and sustain star formation under specific physical conditions. In the Phoenix cluster, efficient gas delivery and a deep gravitational potential contribute to the accumulation of material in the central galaxy. Further analysis shifts from the properties of the central galaxy to the compact region at its core. Material accumulated within Phoenix A is transported towards smaller spatial scales, where additional physical processes influence energy release and mass distribution within the cluster. Unprecedented star formation rates. Deep within Phoenix A, the accumulation of gas does not remain dormant. It undergoes a transformation that is both rapid and extreme, converting raw material into stars at a pace rarely observed in the modern universe. This process, known as star formation, is measured not by isolated events, but by sustained output over time. In Phoenix A, the numbers immediately set it apart. Estimates derived from infrared, ultraviolet, and optical data indicate that the galaxy is forming stars at a rate between 500 and 1,000 solar masses per year. For comparison, the Milky Way forms roughly 1 to 2 solar masses of stars annually. Phoenix A exceeds that rate by several hundred times. These measurements are based on multiple independent indicators. Infrared emission detected by the Hubble Space Observatory reveals large quantities of warm dust heated by newly formed stars. Ultraviolet observations trace the light from massive, short-lived stars that dominate early stellar populations. Optical spectroscopy identifies emission lines associated with ionized gas surrounding star-forming regions. Together, these datasets yield star formation rate estimates for Phoenix A that are significantly higher than those measured in most brightest cluster galaxies. Star formation in Phoenix A is concentrated in the central regions of the galaxy, within an environment surrounded by extremely hot intracluster gas. Under typical conditions, such temperatures inhibit the collapse of gas clouds required for star formation. Observations of many galaxy clusters show that central galaxies usually exhibit little ongoing stellar formation in similar environments. In Phoenix A, however, significant star formation is observed within these central regions. High-resolution imaging reveals that star-forming regions are organized into extended filaments and clumps. These structures stretch tens of thousands of light-years from the galaxy's core, tracing paths where cooler gas has condensed out of the surrounding medium. Observations from the Atacama large millimeter or submillimeter array show that these filaments are rich in molecular hydrogen, the essential ingredient for star formation. The gas densities within them are sufficient to allow gravitational collapse, even as the broader environment remains intensely hot. Estimates place the total cold molecular gas mass in Phoenix A at over 10 to the power of 10 solar masses. Observations indicate that this reservoir is replenished as gas from the surrounding cluster cools and flows inward. In contrast to many isolated starburst galaxies, where gas depletion can occur on timescales of tens of millions of years, Phoenix A retains substantial cold gas over extended periods. Analysis of stellar populations indicates a significant contribution from massive stars with short lifespans. These stars dominate the galaxy's ultraviolet output and inject energy into the surrounding gas through stellar winds and radiation. Their brief lifetimes imply that continued star formation is required to sustain the observed luminosity. Superimposed on this star formation is the presence of dust, an element often overlooked in discussions of galaxy clusters. Dust grains absorb ultraviolet and optical light and re-emit it in the infrared, making them essential tracers of hidden star formation. In Phoenix A, dust masses inferred from infrared data are unusually high for a central cluster galaxy. This dust shields molecular gas from destructive radiation, further enabling star formation to proceed efficiently. The geometry of the star-forming regions provides clues to how this process is regulated. Filaments appear to align with regions of lower gas pressure and cooler temperatures, suggesting that star formation follows pathways carved out by larger-scale dynamics. These structures are not randomly distributed, but are shaped by the movement of gas within the cluster and the gravitational influence of the central galaxy. Their coherence over large distances implies that the underlying conditions supporting star formation are stable over significant periods. Another key factor is the rate at which gas cools from the hot intracluster medium into a form that can form stars. In Phoenix A, this cooling appears unusually efficient. X-ray observations show that gas in the central regions loses energy rapidly, allowing it to condense into colder phases. This process delivers fresh material directly into the star-forming regions, maintaining high production rates. The connection between cooling gas and star formation is direct and observable, making Phoenix A a critical system for studying this relationship. In the early universe, high star formation rates were common as galaxies assembled their stellar mass. At the redshift of Phoenix A, massive galaxies typically exhibit much lower star formation activity. Observations show that Phoenix A maintains star formation rates comparable to those seen in earlier cosmic epochs. Star formation also alters the chemical composition of the galaxy and its surroundings. Massive stars rapidly synthesize heavier elements and disperse them through stellar winds and supernova explosions. Over time, this process enriches the gas with metals, enhancing its ability to cool and collapse further. In Phoenix A, this feedback loop likely contributes to sustaining star formation by improving cooling efficiency. The galaxy thus becomes increasingly capable of converting gas into stars as the process continues. Observations indicate that radiation pressure and stellar winds from young stars disrupt individual gas clouds. However, the inflow of material into Phoenix A continues at rates that exceed the disruptive effects of stellar feedback. In comparison, smaller starburst galaxies often show star formation activity that declines more rapidly following feedback-driven gas disruption. Estimates based on measured gas supply and cooling rates indicate that Phoenix A could sustain high star formation rates for hundreds of millions of years if current conditions persist. This timescale is longer than those inferred for many starburst galaxies. Star formation in Phoenix A occurs alongside energetic processes in the cluster core. Observations show simultaneous heating and cooling of gas, as well as ongoing inflow and disruption within the central regions. These processes operate concurrently rather than reaching a stable equilibrium. Continued observations of Phoenix A provide data on star formation occurring in dense cluster environments. These measurements motivate further investigation of the physical processes that allow gas to cool efficiently in the cluster core, the strongest cooling flow known. The extraordinary rate of star formation in Phoenix A points to a deeper process operating beneath the visible activity. Stars do not form spontaneously. They require a steady supply of cold gas. In the hostile environment at the center of a massive galaxy cluster, the existence of such gas demands an explanation. That explanation lies in a phenomenon known as a cooling flow, and in the Phoenix cluster, this process operates at a scale unmatched anywhere else in the known universe. Galaxy clusters are permeated by hot plasma that emits X-rays as it radiates energy. Over time, this radiation causes the gas to lose heat. In theory, as gas cools, it should sink toward the cluster center under gravity, forming a slow inward flow. Early models predicted that many clusters would host strong cooling flows, depositing vast amounts of cold gas into their central galaxies. However, decades of observations revealed a problem. Most clusters do not show the expected buildup of cold material. Some mechanism was reheating the gas, preventing large-scale cooling. This realization led to the development of feedback models, where energy released by central black holes counteracts cooling and stabilizes the system. X-ray observations indicate that gas in the Phoenix cluster core is cooling at rates of several hundred solar masses per year. This cooling flow delivers material into the central regions, providing gas for ongoing star formation. The measured cooling rate exceeds that observed in most other galaxy clusters. The strength of this cooling flow was first quantified using high-resolution spectroscopy from the Chandra X-ray Observatory. By measuring how X-ray emission changes with temperature, astronomers identified gas transitioning from extremely hot states to cooler ones within a relatively small volume. The data showed a continuous range of temperatures, a signature of ongoing cooling rather than a static configuration. This was a critical finding, as many clusters show truncated temperature distributions that indicate cooling has been interrupted. Phoenix A does not. In the Phoenix cluster, cooling is concentrated within the central few 100,000 light-years. Within this zone, gas densities are high enough that radiative cooling accelerates, creating a positive feedback loop. As gas cools, it becomes denser, which further increases its cooling rate. Observations indicate that this process occurs with minimal suppression from feedback mechanisms. One reason cooling is so effective in Phoenix A is the composition of the intra-cluster gas. X-ray spectra reveal elevated abundances of heavy elements such as iron and silicon. These elements enhance the gas's ability to radiate energy, acting as efficient cooling agents. Their presence reflects a long history of stellar activity and supernova explosions within the cluster, which enriched the gas over billions of years. In Phoenix A, this enrichment appears to have reached levels that significantly amplify cooling efficiency. Another contributing factor is the density profile of the cluster core. Measurements show a steep increase in gas density toward the center, far sharper than in most clusters at similar distances. This concentration of material means that even small temperature drops lead to substantial energy losses. The gravitational potential of the cluster holds the gas in place, preventing it from dispersing as it cools. Instead, cooled material accumulates and flows inward, feeding the central galaxy. The cooling flow in Phoenix A is not a smooth, uniform process. X-ray imaging reveals complex structures within the cooling region, including filaments, clumps, and irregular edges. These features indicate that cooling occurs unevenly, influenced by local variations in density, turbulence, and energy input. Some regions cool faster than others, creating pockets of cold gas embedded within hotter surroundings. This patchwork structure plays a crucial role in shaping where star formation occurs. Velocity measurements of the gas provide further insight. Spectroscopic data indicate that cooled gas moves inward at hundreds of kilometers per second. These flows are guided by the cluster's gravitational field, funneling material toward the central galaxy. Unlike chaotic turbulence that would mix and reheat the gas, these motions appear relatively ordered, allowing cooled material to reach the core without being destroyed. In many clusters, energy input from a central black hole can reheat gas and halt cooling. In Phoenix A, The rate of energy loss through radiation exceeds the local reheating rate, allowing cooling to dominate over large scales. Observations show that cooling and heating processes coexist in the cluster core. Observational evidence supports this imbalance. Temperature profiles show that while some regions are reheated intermittently, the overall trend remains toward cooling. Pressure maps derived from X-ray data reveal zones where gas pressure drops rapidly, consistent with energy being lost faster than it can be replaced. These signatures collectively point to a cooling flow operating near the maximum rate allowed by the cluster's physical conditions. Cooling flows affect mass distribution within clusters, galaxy growth, and black hole feeding. In Phoenix A, the cooling flow transfers material from the intracluster medium into the central galaxy, linking cluster-scale gas with galactic-scale activity. Observed cooling flow rates in other clusters are generally an order of magnitude lower than those in Phoenix A. In several clusters, cooling flows predicted by early models are reduced due to feedback. Phoenix A exhibits cooling flow rates closer to early model predictions. As energy is radiated away, material from larger radii flows inward. This movement alters pressure gradients and can induce instabilities, affecting the structure of the cluster core. The cooling flow supplies gas that supports ongoing star formation and central activity in Phoenix A. Observations indicate that this flow has persisted for hundreds of millions of years. Studying the processes that normally suppress cooling can help explain why this flow remains strong. Observations indicate a compact object at the center of Phoenix A. This source releases energy capable of influencing cooling on cluster-wide scales. Its effects in Phoenix A differ from those seen in most other clusters. The central supermassive black hole. At the very core of Phoenix A lies a supermassive black hole of extraordinary scale, a gravitational behemoth that dominates both the central galaxy and the surrounding intracluster environment. Its existence is not directly observable, yet its influence is undeniable, measurable through the motions of stars, gas, and the energetic phenomena that permeate the cluster's core. Based on dynamical modeling and multi-wavelength observations, its mass is estimated to exceed 10 billion times that of the Sun, a magnitude that places it among the most massive black holes ever identified in the local universe. This mass is not merely a statistic. It defines the gravitational potential well of the galaxy's center, influencing the flow of gas, the dynamics of stellar populations, and the behavior of the hottest plasma in the cluster. The evidence for such a colossal black hole comes from multiple independent methods. High-resolution spectroscopy of the central few hundred light-years of the galaxy reveals stars moving at velocities exceeding 1,000 kilometers per second. Such rapid motion cannot be sustained by the mass of stars alone. The gravitational pull of an unseen object is required. Adaptive optics instruments on the Very Large Telescope and the Keck Observatory have allowed astronomers to resolve the central regions with remarkable precision, confirming the presence of an extremely massive compact object. These measurements align with stellar orbital models that suggest the black hole's sphere of influence extends tens of thousands of light-years from the core, a scale unprecedented in clusters of comparable size. The black hole is actively accreting material, forming a luminous, active galactic nucleus. Gas from the cooling flow spirals inward, losing gravitational potential energy, which is converted into electromagnetic radiation and kinetic energy. X-ray observations show luminosities exceeding 10 to the power of 45 ergs per second, while radio data reveal relativistic jets. The active nucleus interacts with the intracluster medium and molecular gas, driving turbulence, heating plasma, and influencing star formation. The mechanism of accretion is itself remarkable. Gas from the strongest known cooling flow in the universe funnels into the black hole's accretion disk, where gravitational energy heats the material to millions of degrees. Spectroscopy indicates the presence of highly ionized elements, including iron, oxygen, and silicon, moving at thousands of kilometers per second within the inner disk. Such velocities are indicative of material orbiting close to the event horizon, where relativistic effects dominate. Radiation pressure from the inner accretion disk launches outflows that extend tens of thousands of light-years, interacting with the surrounding hot gas and forming cavities detectable in X-ray and radio images. Relativistic jets produced along the black hole's spin axis are some of the most striking features of this system. Observations reveal narrow beams of charged particles traveling at near-light speeds, stretching across distances comparable to the size of the central galaxy itself. These jets displace millions of solar masses of intracluster plasma, inflating cavities that can be traced in X-ray maps. The mechanical energy associated with these jets is immense, estimated to exceed the combined radiative output of the galaxy's stellar population. Yet in Phoenix A, the cooling flow remains largely unimpeded, a rare example of a system where black hole feedback does not fully suppress gas inflow or star formation. The chemical environment near the black hole further amplifies its influence. High-resolution spectroscopy and ALMA observations indicate that the central regions of Phoenix A are enriched with heavy elements, including iron, oxygen, and carbon, as a result of repeated generations of star formation and supernova explosions. These metals enhance the cooling of surrounding gas, making it easier for inflowing material to condense and reach the accretion disk. Molecular gas clumps, with masses ranging from 10 to the power of 6 to 10 to the power of 8 solar masses, orbit the black hole and supply fuel continuously. Their survival in a region dominated by intense radiation and relativistic jets highlights the delicate balance between destructive and constructive forces at play. Comparisons with other central cluster galaxies underscore the extraordinary nature of Phoenix A's black hole. In the Perseus cluster, the central black hole's energy output effectively regulates cooling, limiting star formation to just a few solar masses per year. By contrast, Phoenix A maintains star formation rates exceeding 500 solar masses per year, while the black hole remains active, suggesting that the cooling flow overwhelms feedback mechanisms in certain regions. Such dual growth of both stellar populations and the central black hole is exceptionally rare in the modern universe, providing a natural laboratory for studying the interplay between massive accretion, jet production, and extreme star formation. The black hole's gravitational influence extends beyond gas dynamics into stellar motion and structural evolution. Stars in the innermost kiloparsecs follow rapid, sometimes chaotic orbits shaped by the black hole's mass. Observations suggest that the central galaxy exhibits a dense nuclear component, likely formed through repeated infall of gas and stars funneled by the cluster's potential well. This dense core may enhance the efficiency of gas delivery to the black hole, sustaining the active nucleus over extended timescales. Temporal variability is another defining feature. Long-term X-ray monitoring reveals fluctuations in the nucleus's luminosity on timescales of months to years, corresponding to episodic accretion events. Dense gas, clumps from the cooling flow, occasionally plunge toward the accretion disk, temporarily increasing the energy output and intensifying jet activity. This episodic feeding ensures that the black hole's influence is dynamic, continually reshaping the core environment and affecting both gas distribution and star formation patterns. Magnetic fields play a crucial supporting role in regulating accretion and jet formation. Polarimetric radio measurements indicate coherent magnetic structures aligned with the relativistic jets, helping to collimate particle flows and stabilize the central accretion disk. These fields may also influence molecular gas orbits, preserving dense clumps long enough to feed the black hole while resisting disruption by radiation or shock fronts. Total power from the central black hole, including radiation, jet kinetic energy, and mechanical effects on the intracluster medium, exceeds 10 to the power of 46 ergs per second. This energy output results from sustained accretion supplied by the cooling flow. Observations show that stellar and black hole growth occur concurrently at high rates in Phoenix A. The supermassive black hole influences the surrounding galaxy and cluster environment. Its mass, energy output, and interaction with inflowing gas from the cooling flow affect star formation, gas dynamics, and cluster processes. Relativistic jets across the cluster. From the very heart of Phoenix A, the supermassive black hole launches colossal jets of charged particles that move at nearly the speed of light, stretching far beyond the confines of the central galaxy and into the surrounding cluster. These relativistic jets are not merely byproducts of accretion. They are primary channels for energy transport, shaping the intracluster medium over hundreds of thousands of light years. Observations with the Very Large Array, the Australia Telescope Compact Array, and the Atacama Large Millimeter or Submillimeter Array reveal that the jets maintain remarkable collimation over distances exceeding 120,000 light-years, an exceptional scale for any known cluster. Their influence dominates the dynamics, chemistry, and structure of the central regions, making them one of the defining characteristics of Phoenix A's violent environment. X-ray and radio observations indicate that the jets carry kinetic power exceeding 10 to the power of 46 ergs per second. The jets displace intracluster gas, forming cavities observable as depressions in X-ray brightness. Each cavity contains millions of solar masses of plasma, with volumes approaching 10 to the power of 73 cubic centimeters. The energy input drives pressure waves at hundreds of kilometers per second, heating regions, inducing turbulence, and affecting gas distribution in the cluster core. Along the jets, astronomers observe a series of bright knots, regions where particle acceleration is particularly intense. High-resolution radio imaging shows that these knots are spaced at intervals of several thousand light-years and move outward from the black hole at relativistic speeds. The knots are transient features. They represent episodes of increased activity, likely linked to fluctuations in accretion rate. X-ray observations confirm that some knots coincide with regions of shock-heated gas, where the jets compress surrounding plasma and accelerate particles to energies exceeding 10 to the power of 15 electron volts. These processes contribute not only to heating the intracluster medium, but also to producing high-energy cosmic rays that pervade the cluster. The interaction between the jets and the surrounding gas is multifaceted. As the relativistic streams collide with dense filaments of hot plasma, they generate cavities and shock fronts, while simultaneously compressing molecular clouds and denser regions of the intracluster medium. Observations with ALMA reveal molecular clumps of 10 to the power of 6 to 10 to the power of 8 solar masses positioned along or near jet paths, indicating that some dense gas survives despite extreme mechanical forces. The compression can enhance star formation locally, creating regions where stellar birth rates temporarily spike, while in adjacent areas, the same shocks can disrupt clouds, dispersing material and preventing collapse. This duality illustrates the complex role of jets as both destructive and constructive agents in Phoenix A. Magnetic fields play a critical role in shaping the jet's structure and influence. Polarimetric radio observations indicate that coherent fields run along the jet axis, helping to collimate the flow over immense distances. These fields also stabilize the surrounding plasma, preventing instabilities that would otherwise disrupt the jets. In addition, magnetic reconnection events within the jets likely contribute to the formation of bright knots and episodic outbursts of particle acceleration. Observed Faraday rotation measures suggest field strengths on the order of tens of microgauss, consistent with highly organized and energetically significant magnetic structures in the cluster core. Precession of the jets provides additional insight into the behavior of the central black hole. Multi-epoch imaging shows subtle changes in jet orientation over millions of years, likely resulting from a misalignment between the black hole's spin axis and the angular momentum of infalling gas. This slow precession allows the jets to sweep across different regions of the cluster, distributing energy more evenly and affecting the density and temperature structure of the surrounding medium. Such sweeping is rare in cluster jets and contributes to the chaotic environment that allows Phoenix A to sustain both extreme star formation and powerful, active galactic activity simultaneously. Chemical enrichment along the jet paths further emphasizes their importance. Spectroscopic studies reveal elevated abundances of iron, silicon, and oxygen in cavities and filaments aligned with the jets. These metals originate from supernovae in the central galaxy, yet the jets transport them over tens of thousands of light years, enriching regions of the intracluster medium far beyond the immediate vicinity of the galaxy. This redistribution affects cooling rates locally, enabling pockets of gas to condense more efficiently and feed both star formation and black hole accretion. It is a rare case in which feedback simultaneously disperses and organizes matter, shaping the violent environment on multiple scales. The jet's influence is evident in X-ray and gamma-ray observations. Chandra imaging reveals shock fronts coinciding with the jet paths where gas is heated to tens of millions of degrees. Fermi Space Telescope data detect gamma-ray emission consistent with cosmic ray acceleration within these shocks. Electrons and protons accelerated to energies exceeding 10 to the power of 15 electron volts contribute to non-thermal pressure support in the intracluster medium, influencing overall gas dynamics. The combination of mechanical, thermal, and non-thermal energy transfer establishes the jets as dominant agents, shaping the cluster's physical and energetic environment. Temporal variability is a defining characteristic of the jets. Light curves and multi-epoch radio maps show episodes of heightened activity lasting millions of years, followed by quieter phases. Each active period inflates new cavities, generates shock waves, and injects fresh energy into the intracluster medium. Older cavities persist, overlapping with new ones, creating a complex, layered structure in which multiple generations of jet activity coexist. This temporal layering amplifies turbulence, sustains ongoing star formation, and produces a patchwork of high and low-density regions that continue to feed the central black hole. Observations indicate that the jets transport energy and momentum over distances exceeding 500,000 light-years, influencing gas inflow patterns and the distribution of hot plasma throughout the cluster. The jets affect the physical, chemical, and dynamic state of the intracluster medium on large scales. The relativistic jets of Phoenix A act as conduits for energy and particle acceleration. They inflate cavities, trigger turbulence, redistribute metals, and compress molecular clouds, affecting star formation and accretion simultaneously. Observations show that the jets influence the cluster core over hundreds of thousands of light years, maintaining motion, heating, and chemical enrichment. Observations of these jets provide context for studying black hole feedback in Phoenix A, including its interaction with the strongest cooling flow and continued star formation despite a supermassive, highly active black hole. Breakdown of black hole feedback. Phoenix A challenges everything astronomers know about galaxy cluster regulation. In most clusters, the supermassive black hole at the core exerts immense influence, regulating the surrounding gas through energetic feedback. This feedback typically suppresses runaway cooling and star formation, maintaining a delicate balance over billions of years. Yet in Phoenix A, this mechanism appears to falter. The central black hole, with a mass estimated at more than 10 billion times that of the Sun, produces extraordinary energy in the form of radiation, jets, and outflows. Yet the cluster's cooling flows persist at rates of thousands of solar masses per year. Star formation continues at over 500 solar masses annually, an anomaly in galaxy cluster cores of this scale and age. Understanding this breakdown reveals how extreme conditions can overwhelm even the most powerful black hole engines. X-ray observations provide direct evidence of the failure of feedback. Chandra imaging shows hot plasma in the cluster core with temperature gradients from 10 million to over 15 million Kelvin. Yet the gas is far from quiescent. Turbulent motions measured through Doppler shifts indicate velocities exceeding 300 kilometers per second in localized regions. In a well-regulated cluster, jets and outflows heat the surrounding plasma efficiently, creating cavities and shock fronts that prevent gas from cooling. In Phoenix A, these features exist, but their effects are insufficient. The volume of gas cooled and condensed far exceeds the energy injected by the black hole, allowing dense molecular clouds to accumulate and feed both star formation and the central black hole itself. The mechanical energy of relativistic jets, measured at over 10 to the power of 46 ergs per second, interacts with the intracluster medium in complex ways. While jets create cavities observable in X-ray maps and propagate shock fronts, much of the surrounding plasma remains unaffected. Detailed analysis indicates that the cavities represent only a fraction of the dense gas volume. The jet's energy is highly directional, concentrated along narrow paths, leaving vast reservoirs of cold gas untouched. This anisotropic distribution allows cooling to proceed unimpeded in many regions, demonstrating that jet power alone does not guarantee regulation, especially in clusters with extreme inflow rates like Phoenix A. The cooling flow itself is exceptional. Observations reveal that the central regions have gas densities around 0.05 particles per cubic centimeter, far higher than most cluster cores. This density enables rapid radiative cooling, with energy losses exceeding the heating delivered by the black hole. Molecular gas clumps with masses between 10 to the power of 7 and 10 to the power of 8 solar masses, detected by ALMA, orbit within a few kiloparsecs of the black hole. These clumps are dense enough to survive the destructive forces of relativistic jets and radiation pressure, illustrating how Phoenix A maintains a continuous reservoir of star-forming material despite the enormous energy output of its central engine. Chemical composition further underscores the feedback breakdown. High-resolution spectroscopy of the intracluster medium shows iron, silicon, and oxygen abundances more than twice the solar value in the central kiloparsecs. Normally, feedback mechanisms disperse these metals throughout the cluster, preventing localized overcooling. In Phoenix A, however, enriched gas remains concentrated near the galaxy's core, facilitating rapid molecular cloud formation and continuous fueling of star formation. The combination of high metallicity and dense gas produces radiative cooling rates among the highest ever observed in a galaxy cluster. Turbulence generated by the jets has paradoxical effects. Far from halting cooling, turbulence compresses certain gas filaments, triggering local star formation events. X-ray spectroscopy reveals velocity dispersions exceeding 200 km per second along jet-affected regions. These fluctuations create a chaotic environment where some gas is heated and displaced, while other regions are compressed and destabilized, leading to episodic bursts of star formation. This dual role of feedback as both inhibitor and enabler demonstrates the unique conditions that allow Phoenix A to remain highly productive despite the presence of an active supermassive black hole. Temporal variability of black hole activity contributes to the breakdown. Multi-epoch observations reveal periods of intense jet activity interspersed with quiescent phases lasting millions of years. During active phases, cavities expand, shock waves propagate, and turbulence increases, temporarily heating portions of the intracluster medium. However, the periods of inactivity allow cooling to dominate, enabling gas accumulation and star formation to continue. This episodic nature prevents the black hole from maintaining a steady regulatory influence, creating a cyclical pattern of heating and cooling unique to extreme clusters like Phoenix A. Magnetic fields also influence feedback efficiency. Polarimetric radio observations indicate strong, coherent fields aligned with the jets, which help to collimate the outflows. While these fields maintain the jet's structure over immense distances, they also confine energy to narrow channels, limiting the volume of gas affected. As a result, large reservoirs of dense gas remain outside the jet's influence, continuing to cool and feed the central galaxy. This effect highlights the complex interplay between mechanical energy, magnetic structure, and gas dynamics in extreme cluster environments. Observations indicate that Phoenix A's central galaxy has formed tens of billions of solar masses of stars over the past few 100 million years. The black hole continues to accrete, fed by the same cooling flows it does not suppress. This dual growth of stars and the supermassive black hole occurs in an environment with high density, high inflow conditions, showing that feedback mechanisms may be limited under extreme circumstances. In Phoenix A, high metallicity gas remains concentrated near the core, unlike in clusters where feedback disperses metals. This localized enrichment increases cooling, supporting continued molecular cloud formation and star formation. Observed abundances of oxygen and iron in the central kiloparsecs exceed 1.5 times solar values, demonstrating ongoing metal enrichment and recycling in the cluster core. Energy redistribution from the black hole is uneven. Jets create cavities, inflate bubbles, and drive shocks, but large regions of the intracluster medium remain relatively undisturbed. X-ray imaging shows dense filaments threading through heated regions, resisting disruption by jets or radiation. Gas continues to cool, forming molecular clouds and supporting high star formation rates. Episodic jet activity, magnetic confinement, anisotropic energy distribution, and dense inflows limit the effectiveness of traditional feedback models under these conditions. In Phoenix A, the strongest known cooling flows persist despite the central black hole's mass and energetic output, producing star formation and continued accretion at high rates. High gas density, anisotropic jets, episodic activity, strong magnetic fields, and enriched chemical environments contribute to the limits of traditional feedback mechanisms. The cluster provides an environment for observing high-energy physical processes in action, record-breaking cluster temperatures, Phoenix A is a galaxy cluster that defies conventional understanding of intracluster environments, particularly through its extreme thermal conditions. Unlike most clusters, where core temperatures average between 5 and 10 million Kelvin, Phoenix A exhibits plasma exceeding 15 million Kelvin in its central regions, with localized hotspots surpassing 20 million Kelvin. These values are extraordinary for any galaxy cluster in the nearby universe, and they place Phoenix A among the most thermally violent cosmic structures ever observed. Detailed measurements come from high-resolution X-ray spectroscopy, particularly from the Chandra X-ray Observatory's Advanced CCD Imaging Spectrometer, XMM-Newton's European Photon Imaging Camera, and NuSTAR observations. These instruments detect emission lines from highly ionized elements such as iron, silicon, sulfur, and oxygen, allowing astronomers to map temperature variations with precision on scales as small as a few kiloparsecs. By analyzing the ratios of these lines, scientists have uncovered steep thermal gradients and a complex interplay between hot plasma, cooler filaments, and shock-heated regions, revealing the chaotic thermal environment of Phoenix A. The temperature extremes are associated with the cluster's central black hole and its jets. The black hole, with a mass exceeding 10 billion solar masses, injects kinetic energy into surrounding gas, inflating cavities and generating shock waves that propagate through the intra-cluster medium. Observations indicate that these shocks move at speeds exceeding 1,500 kilometers per second, locally heating plasma to over 20 million Kelvin. X-ray surface brightness maps reveal overlapping shocks within the core, producing turbulence and complex flows that distribute heat. Dense molecular filaments in the core, each containing millions of solar masses of gas, remain cooler than 5 million Kelvin, showing the coexistence of extreme heating and localized cooling. Similar contrasts occur in clusters such as Perseus or Abell 1795. The core of Phoenix A exhibits steep temperature gradients over relatively short distances. Within the inner 50 kiloparsecs, temperatures can vary by more than 10 million Kelvin. In most clusters, thermal conduction and turbulent mixing smooth such differences, creating more homogeneous cores. In Phoenix A, dense gas filaments, episodic jet outflows, and magnetic field confinement maintain these variations. Magnetic field strengths in the core have been measured at tens of microgauss, strong enough to inhibit thermal conduction along certain axes while allowing heat transport along aligned field lines. Observations from the Very Large Array and ALMA indicate that these magnetic fields guide plasma flows and filament alignment, producing a mix of hot, turbulent gas interspersed with cooler, star-forming filaments. Observations of velocity dispersions provide further insight into the extreme temperatures. Spectroscopic data from Chandra and XMM-Newton indicate that turbulent motions in the hot plasma exceed 1,000 kilometers per second in the central regions. Such turbulence arises from a combination of gravitational interactions, mergers, infalling galaxies, and energy input from the black hole. These chaotic motions amplify heating through viscous dissipation, contributing to the unusually high plasma temperatures observed. In comparison, relaxed clusters of similar mass rarely exceed dispersions of 400 to 600 kilometers per second, highlighting the exceptional energy present in Phoenix A. In addition, measurements of line-of-sight velocities in the intracluster medium show rapid bulk flows of 600-800 kilometers per second, consistent with the propagation of shock fronts and cavity inflation throughout the cluster core. Temperature extremes affect chemical evolution within the cluster. X-ray spectroscopy indicates iron, silicon, and oxygen abundances in the core exceed 2 to 3 times solar values. While hot plasma spreads metals across tens of kiloparsecs, dense cold filaments retain enriched gas, accelerating molecular cloud formation and sustaining high star formation rates. Observations suggest that the central galaxy has formed tens of billions of solar masses of stars over the past 200 million years. Supernovae occurring within the filaments inject energy locally, contributing to turbulence and mixing while filaments remain dense and cool. Shock fronts are observed through surface brightness discontinuities, temperature jumps, and Doppler-broadened emission lines. Shocks create pockets of superheated plasma while compressing adjacent filaments. Analysis indicates shocks propagate radially from the central galaxy at speeds up to 1,500 kilometers per second, locally increasing temperatures by several million Kelvin. These shocks often occur in conjunction with jet-driven cavities, producing turbulent eddies in the surrounding plasma. In some regions, shock fronts extend over 100 kiloparsecs, influencing the central galaxy, satellite galaxies, and dense gas clumps. Peripheral regions of Phoenix A, extending beyond 500 kiloparsecs, show lower temperatures, averaging 5 to 6 million Kelvin. Yet localized hotspots persist due to turbulence from mergers and the infall of subclusters. Observations suggest that these outer regions remain thermally active, with velocity dispersions of 500 to 700 kilometers per second. These outer regions also show evidence of minor shock heating and residual turbulence from prior mergers. Hot plasma prevents collapse in low-density regions, while dense filaments condense rapidly, forming molecular clouds. Cooling times vary. High-density filaments can cool in tens of millions of years, while low-density plasma remains superheated for over 1 billion years. ALMA observations of molecular gas dynamics indicate that filament collapse is episodic, often triggered by pressure waves from shock fronts or jet outflows. Extreme temperatures also enhance X-ray luminosity. Phoenix A emits over 10 to the power of 45 ergs per second, predominantly from highly ionized iron and silicon in the central regions. The intensity of this emission is directly linked to shock heating, turbulence, and jet-driven cavity inflation. Observations using Suzaku and NuSTAR have revealed that the cluster's hard X-ray spectrum contains evidence of non-thermal emission, likely originating from accelerated particles in shocks. By comparing these measurements with other massive clusters such as Abell 1835 and RxJ 1347, 5 to 1145, astronomers have concluded that Phoenix A represents the upper extreme of cluster heating in the nearby universe. The thermal environment of Phoenix A influences its evolution. High plasma temperatures, turbulence, shock propagation, and localized cooling drive star formation, black hole growth, and chemical enrichment. Over hundreds of millions of years, these processes sustain an active core, forming new stars at rates exceeding 500 solar masses per year while feeding a very massive black hole. Extreme X-ray emission. The extraordinary temperatures in Phoenix A produce a corresponding intensity of X-ray emission, making the cluster one of the brightest X-ray sources ever observed. Observations reveal luminosities exceeding 10 to the power of 45 ergs per second in the 0.510 keV band, a value unmatched by most known galaxy clusters. The primary mechanism behind this radiation is thermal bremsstrahlung, the emission from highly ionized plasma at tens of millions of Kelvin, combined with line emission from elements such as iron, silicon, sulfur, and oxygen. Using the Chandra X-ray Observatory's advanced CCD imaging spectrometer, XMM-Newton's European photon imaging camera, and NuSTAR's focal plane modules, astronomers have constructed detailed spectral maps that trace both the spatial distribution and energy dependence of the X-rays, revealing a patchwork of high luminosity regions centered around the cluster core and extending outward along cavities, filaments, and shock fronts. These maps provide spatial resolutions down to a few kiloparsecs, allowing scientists to identify variations in both plasma temperature and chemical composition. NuSTAR observations, in particular, have uncovered a hard X-ray component indicating the presence of non-thermal emission likely caused by relativistic particles accelerated in shocks and jet interactions, adding a high-energy layer to the cluster's radiation output. The central galaxy contributes the majority of the X-ray output, but the cluster as a whole participates in the radiative display. Within the inner 100 kiloparsecs, surface brightness peaks reach 10 to the power of negative 12 ergs per square centimeter per second per arc second squared, comparable to the brightest regions in the Perseus cluster and far exceeding the average of nearby massive clusters. The distribution of X-ray intensity closely aligns with cavities inflated by the central black hole's relativistic jets, revealing direct coupling between energy injection and radiation production. Observations show that each cavity displaces tens of billions of solar masses of plasma, and the associated shocks propagate outward at 1,500 kilometers per second, heating surrounding gas to levels sufficient to produce localized X-ray flares. High-resolution Chandra imaging further shows ripples, eddies, and filamentary structures in X-ray brightness, which trace turbulence in the plasma and the movement of shock-heated gas. These complex structures offer a visual record of the continuous energy redistribution occurring within Phoenix A. Spectroscopy of the X-ray emission provides a detailed view of the plasma's chemical composition and temperature distribution. Iron in the Fe-XXV and Fe-XX6e ionization states dominates high-energy emission, indicating central temperatures exceeding 15 million Kelvin. Silicon, sulfur, and oxygen lines confirm heavy element abundances, with measured metallicities ranging from 2 to 3 times solar. These elevated abundances result from a combination of ongoing star formation in the central galaxy and repeated supernova activity over the past 200 million years. The X-ray emission allows astronomers to trace metal movement throughout the cluster, revealing gradients in enrichment between the core, filaments, and outer regions. Heavy elements are transported by turbulence, shocks, and inflowing subclusters, creating spatial variations in metallicity over scales of hundreds of kiloparsecs. This distribution of metals also provides insight into the past activity of the central black hole and the cumulative effect of feedback processes over cosmic time. The hard X-ray component, observed primarily by NuSTAR, indicates the presence of non-thermal processes alongside thermal emission. Relativistic electrons, accelerated in shocks and jet interactions, produce inverse Compton scattering of cosmic microwave background photons, generating X-rays above 10 keV. This component is evident near cavity rims and shock fronts, where energy densities are highest and plasma velocities exceed 1,500 kilometers per second. Regions along jet axes and cavity boundaries show X-ray excesses of up to 30% compared to surrounding plasma. Clusters such as Abell 1835, Abell 2390, and RxJ 1347, 5 to 1145, display bright X-ray cores. Yet their luminosities rarely exceed 10 to the power of 44 ergs per second, and their non-thermal contributions are weaker. Phoenix A's combination of thermal emission and detectable non-thermal X-rays places it at the upper range of known galaxy clusters. Detailed surface brightness profiles indicate a rapid decline beyond 500 kiloparsecs. Yet filaments and peripheral shocks maintain localized X-ray enhancements. These extended features are associated with minor mergers and the accretion of smaller galaxy groups. Observations show that outer, shock-heated regions can span up to 800 kiloparsecs, creating pockets of enhanced X-ray emission beyond the central galaxy. The central supermassive black hole is a major driver of X-ray emission. Accretion of dense molecular gas generates high-energy photons that interact with surrounding plasma to create regions of enhanced ionization. Observations indicate that the accretion rate may reach tens of solar masses per year, sufficient to power the observed X-ray luminosity. Jets emerging from the black hole contribute to cavity formation, shock generation, and local heating, all of which amplify X-ray emission. Radio observations from the Very Large Array reveal that these jets extend over hundreds of kiloparsecs, closely tracing the edges of X-ray cavities, while ALMA observations show molecular filaments aligned along the same axis, indicating a direct relationship between jet activity, gas dynamics, and X-ray production. The mechanical power of these jets is estimated to exceed 10 to the power of 45 ergs per second, confirming their dominant role in shaping the X-ray properties of the cluster. Thermal instabilities within the intra-cluster medium create additional complexity in X-ray emission. Dense filaments can survive in proximity to million-degree plasma, and when shocks or turbulence compress these filaments, localized X-ray enhancements occur. Chandra imaging demonstrates that filaments can reach tens of kiloparsecs in length while maintaining cooler cores, with temperatures in some cases below 5 million Kelvin. Surrounding plasma remains superheated, producing high-intensity X-rays that trace the boundaries of these cold structures. Observations spanning over a decade reveal episodic brightening in cavity rims and shock fronts, suggesting that energy injection from the central black hole occurs in bursts. Episodic outbursts drive waves of heating through the intra-cluster medium, producing transient increases in X-ray intensity. Monitoring with Chandra, combined with high-cadence XMM-Newton spectroscopy, shows some regions brightening by 10–20% over several million years. These variations provide information on the timing and scale of jet activity and accretion events. X-ray emission contributes to gas heating, ionization, and turbulence, influencing star formation and black hole feeding cycles. Dense filaments shield gas locally, allowing star formation while the surrounding hot plasma regulates the cluster's thermal stability. High X-ray luminosity, non-thermal emission, shock propagation, and filamentary structures are associated with these processes, near maximum accretion activity. At the core of Phoenix A lies a supermassive black hole whose feeding behavior defies expectations for clusters of its type. Observational data indicate that this black hole is accreting at rates near its theoretical Eddington limit, with estimates ranging from 20 to 40 solar masses per year. Such a rate is extraordinary, as most central cluster black holes accrete at only a fraction of their maximum potential. X-ray and radio observations reveal the complex interplay between this extreme feeding process and the surrounding intracluster medium. The black hole's accretion disk, extending several hundred astronomical units, emits across the electromagnetic spectrum, with particularly intense outputs in the X-ray, ultraviolet, and optical bands. NuSTAR and Chandra data indicate that hard X-ray emission originates from the innermost regions of the accretion disk, where temperatures exceed hundreds of millions of Kelvin, providing direct evidence of relativistic processes near the event horizon. The high accretion rate sustains continuous jet activity, with bipolar outflows extending hundreds of kiloparsecs into the intra-cluster medium. These jets are highly collimated and maintain velocities approaching 0.95 times the speed of light, as inferred from radio interferometry using the Very Long Baseline Array. Their mechanical power exceeds 10 to the power of 45 ergs per second, sufficient to inflate multiple X-ray cavities observed in the surrounding hot plasma. Observations show that these cavities have diameters ranging from 20 to 50 kiloparsecs, and in some cases overlap to form interconnected structures spanning more than 100 kiloparsecs. As these jets propagate, they drive shock fronts that heat the intracluster medium, disrupt filamentary structures, and trigger localized turbulence, which in turn influences the accretion process by regulating gas inflow toward the black hole. Spectroscopy of the accretion disk provides insights into its structure and composition. Emission lines from highly ionized iron, oxygen, and neon indicate a disk rich in heavy elements, consistent with continuous inflow from the enriched intracluster medium. Observations with XMM-Newton and the Hubble Space Telescope reveal a stratified temperature profile within the disk, with inner regions exceeding 10 to the power of 8 Kelvin, while outer regions remain below 10 to the power of 7 Kelvin. These temperature differences correspond to variations in density and viscosity, which in turn influence the efficiency of angular momentum transport. The presence of dense molecular clouds in proximity to the central black hole adds further complexity. ALMA observations show that filaments of molecular gas, each containing millions of solar masses, spiral inward along magnetic field lines, delivering cold gas to the accretion disk and sustaining high accretion rates over extended periods. Temporal variability of emitted radiation is observed from the central black hole. Long-term monitoring with Chandra and XMM-Newton demonstrates episodic flares, with X-ray luminosity increasing by 15–25% over timescales of tens of millions of years. These fluctuations correspond to bursts of enhanced gas inflow or instabilities within the accretion disk. Radio observations indicate corresponding increases in jet luminosity, showing the connection between accretion rate and mechanical energy output. In Phoenix A, these mechanisms do not fully suppress inflow, allowing near maximal accretion to persist. Gas inflow toward the central black hole is influenced by both large-scale cluster dynamics and small-scale interactions. Infalling galaxy groups contribute material, with individual galaxies losing gas through ram pressure stripping as they traverse the hot intracluster medium. Observations of stripped tails using the Hubble Space Telescope and Chandra reveal streams containing tens of millions of solar masses of ionized and neutral gas, which gradually migrate toward the cluster core. This external supply enhances the black hole's accretion reservoir, supporting sustained near-maximal feeding over hundreds of millions of years. Accretion processes in Phoenix A are linked to the cluster's star formation activity. The central galaxy exhibits a star formation rate exceeding 500 solar masses per year. ALMA and Herschel observations reveal massive molecular clouds within the inner 50 kiloparsecs, with densities above 10 cubed particles per cubic centimeter, providing fuel for star formation and material for accretion. As gas collapses to form stars, feedback from supernovae injects turbulence into surrounding filaments, influencing inflow to the central black hole. X-ray and optical observations show that these processes occur simultaneously. Relativistic effects near the black hole further amplify the energetic environment. The inner accretion disk experiences frame dragging due to the black hole's spin, with estimates suggesting a dimensionless spin parameter exceeding 0.9. This rapid rotation enhances magnetic field amplification, driving stronger jet collimation and more efficient extraction of rotational energy. Observations of radio polarization confirm highly ordered magnetic fields along jet axes, while X-ray spectroscopy indicates Doppler broadening consistent with relativistic orbital motion within the disk. These effects ensure that energy from the black hole is efficiently transferred into both radiation and mechanical outflows, sustaining the extreme conditions observed in Phoenix A. Numerical modeling of Phoenix A's accretion processes shows the requirements for sustaining near maximal rates over long timescales. Simulations using adaptive mesh refinement codes show that gas inflow must overcome angular momentum barriers, turbulence, and pressure gradients to reach the black hole. In Phoenix A, the combination of dense molecular filaments, ongoing mergers, and cavity-driven turbulence facilitates continuous inflow, supporting sustained high accretion. Models predict that without such conditions, accretion rates would decline by an order of magnitude. High-resolution imaging also reveals episodic outflows from the accretion disk itself. Observations indicate winds emanating at velocities of 500, 1,000 km per second, carrying both ionized and neutral gas into the surrounding cluster medium. These disk winds interact with jet-driven cavities and filaments, producing shocks that contribute to X-ray emission and further regulate the distribution of gas. The interplay between inflow, outflow, and jet activity creates a highly dynamic environment in which gas is continuously recycled between the black hole, central galaxy, and surrounding intracluster medium. Finally, the near maximum accretion activity in Phoenix A contributes to turbulence, drives shocks, and enriches the intracluster medium with metals from both the accretion disk and associated star formation. Observations of chemical abundances, plasma temperatures, and X-ray emission patterns indicate that this activity has persisted for at least 200 million years. Mechanical feedback, radiation, and continued gas inflow characterize the cluster core. Shock fronts in the intracluster medium. In Phoenix A, the intracluster medium is far from static. High-resolution observations reveal a complex network of shock fronts propagating across hundreds of kiloparsecs, a direct consequence of both central black hole activity and ongoing galaxy interactions. Using Chandra and XMM-Newton, astronomers have detected multiple shock fronts with Mach numbers ranging from 1.5 to 2.5, indicative of supersonic disturbances traveling through the hot plasma. The shocks are not uniform. Instead, they form arcs and ripples that often coincide with X-ray cavities and radio jet structures. Some of these fronts extend over 400 kiloparsecs from the central galaxy, producing local increases in plasma temperature by several million Kelvin. Observations in the soft X-ray band reveal enhanced emission along these arcs, corresponding to compressed and heated gas. The velocities associated with these shock fronts vary widely. In the inner 50 kiloparsecs, velocities reach 1,500 km per second, driven primarily by energy injection from the central supermassive black hole. Further out, the shocks decelerate as they propagate through lower density regions, but still maintain speeds of 800, 1,200 km per second. These shocks contribute significantly to the redistribution of energy within the cluster, converting mechanical energy from jets and cavity inflation into thermal energy in the plasma. Observations of temperature jumps across the shock boundaries show increases of 20–30%, confirming their energetic impact on the intracluster medium. Shock fronts in Phoenix A influence the cluster's filamentary structures. ALMA and Hubble Space Telescope imaging reveal that dense molecular filaments are often aligned along or perpendicular to shock fronts. When shocks compress these filaments, local star formation rates increase, with new stars forming at rates exceeding 100 solar masses per year in some regions. These filaments, containing millions of solar masses of molecular gas, act as conduits for material to flow toward the central galaxy while being shaped by the shocks. X-ray spectroscopy provides further evidence of shock-driven heating. Emission lines from highly ionized iron, silicon, and sulfur show broadened profiles along shock fronts, corresponding to turbulent velocities of 300–500 km per second. These broadened lines indicate that shocks not only heat the gas, but also inject turbulence, creating eddies and vortices that persist for tens of millions of years. The resulting turbulence contributes to the mixing of metals throughout the intracluster medium, enhancing the uniformity of chemical abundances over large scales. Observations indicate that metallicity in shock-affected regions can be up to 2.5 times solar, reflecting the enrichment from both ongoing star formation and past supernova events in the central galaxy. The morphology of shock fronts provides information about the history of energy injection in Phoenix A. Deep Chandra imaging shows concentric ripples centered on the core, consistent with repeated outbursts from the black hole over the past 200 million years. Each outburst produces a new set of shock fronts, with outer fronts representing earlier events and inner fronts tracing more recent activity. Radio observations with the Very Large Array confirm that these shocks coincide with regions of jet activity. The shocks maintain turbulence, affect cooling of the central gas, and influence X-ray luminosity of the cluster. Shocks also result from minor mergers and in falling galaxy groups. Optical spectroscopy of member galaxies using the Very Large Telescope and Keck Observatory reveals that several small groups are falling into Phoenix A at velocities of 1,500 km per second relative to the cluster core. As these groups interact with the hot intra-cluster medium, bow shocks form ahead of them, compressing gas and creating localized enhancements in X-ray emission. Observations indicate that these merger-driven shocks can extend over 200 kiloparsecs, producing temporary pockets of dense, heated gas that can trigger additional star formation or contribute to gas inflow toward the central galaxy. Such interactions emphasize that shock formation in Phoenix A is not solely the result of central black hole activity, but also of ongoing cluster assembly. Estimates from Chandra and XMM-Newton suggest that the total mechanical energy deposited into the intracluster medium by shocks exceeds 10 to the power of 60 ergs, comparable to the total thermal energy of the plasma in the central 500 kiloparsecs. This energy is distributed across multiple fronts, ripples, and cavities, with individual shocks contributing between 10 to the power of 58 and 10 to the power of 59 ergs. Dissipation of this energy heats the gas and generates pressure gradients that drive turbulence and bulk motions, redistributing energy within the cluster. Observations reveal secondary phenomena associated with shocks, including weak shocks, sound waves, and sloshing motions of the intracluster medium. Weak shocks with Mach numbers below 1.3 are often difficult to detect but contribute to heating and mixing the plasma. Sound waves, identified through ripples in X-ray surface brightness, transport energy outward from the core, while sloshing motions, triggered by minor mergers or asymmetrical energy injection, create oscillations in the gas that enhance turbulence and filament formation. Shock fronts affect star formation in the central galaxy and its surroundings. When shocks compress dense molecular clouds, the local gene's mass decreases, facilitating the collapse of gas into new stars. Observations with ALMA indicate that some filaments affected by shocks show star formation efficiencies up to 50% higher than unshocked regions. Hubble imaging confirms the presence of young, massive star clusters along the paths of prominent shocks with ages less than 10 million years. Time evolution of shock fronts is also observable. Multi-epoch Chandra and XMM-Newton data show that inner shocks move outward at speeds of 1,500 kilometers per second, while outer shocks decelerate over hundreds of millions of years. By comparing surface brightness and temperature profiles across epochs, astronomers can reconstruct the sequence of energy injection events and estimate the timing of black hole outbursts. These measurements suggest that the central black hole has experienced repeated active phases every 5,100 million years, each generating new shock fronts that propagate through the intracluster medium. Black hole-driven and merger-driven shocks contribute to heating gas and redistributing energy. Shock fronts also transport metals, trigger star formation, and influence X-ray luminosity throughout the core and surrounding filaments. Dark matter structure of the cluster. Beneath the luminous chaos of Phoenix A lies a hidden scaffolding that dictates the cluster's extreme behavior, its dark matter halo. Invisible to all but gravitational probes, dark matter forms the majority of the cluster's mass, shaping the motion of galaxies, the distribution of hot gas, and the propagation of shock fronts. Gravitational lensing studies, conducted using the Hubble Space Telescope's Advanced Camera for Surveys and the European Southern Observatory's Very Large Telescope, reveal that Phoenix A possesses one of the most massive dark matter halos ever measured. Total mass estimates reach approximately 2 × 10⁻15 solar masses within a radius of 2 megaparsecs, with dark matter comprising more than 80% of this total. The gravitational influence of this enormous halo maintains the high velocity dispersions of the cluster's galaxies, measured at 1,201,400 kilometers per second, while simultaneously confining the hot X-ray emitting plasma observed in previous chapters. Strong and weak lensing analyses reveal intricate substructure within the dark matter halo. High-resolution maps show multiple dense clumps, often coinciding with galaxy overdensities and minor merging subclusters. These subhalos, each with masses ranging from 10 to the power of 12 to 10 to the power of 13 solar masses, create localized distortions in light from background galaxies, allowing astronomers to reconstruct the three-dimensional mass distribution. Dense concentrations create local potential wells that funnel intracluster gas and molecular filaments toward the core. Observations indicate that the densest clumps lie within 300 kiloparsecs of the central galaxy, coinciding with regions of high X-ray luminosity and active star formation. The overall halo exhibits a pronounced cusp at the center, consistent with Navarro-Frank white profiles observed in massive clusters, yet the scale radius appears unusually compact for a system of Phoenix A's mass. This compactness enhances gravitational confinement of the intracluster medium, contributing to high central gas densities exceeding 0.1 particles per cubic centimeter. As a result, cooling flows, jet-driven shocks, and turbulence operate in an environment where gravitational potential dominates over thermal pressure, amplifying the efficiency of energy transfer from black hole outflows to the surrounding gas. Detailed modeling shows that the gravitational acceleration near the core exceeds 10 to the power of -8 centimeters per second squared, strong enough to sustain high-density filaments despite extreme heating from X-rays and shocks. These conditions also stabilize cold molecular clouds against disruption, allowing them to spiral inward along gravitational channels toward the central supermassive black hole. Dark matter influences the cluster's rotational and velocity structure. Spectroscopic surveys of over 200 member galaxies using Keck Observatory and Gemini North show coherent bulk motions aligned with the halo's elongated axis. These motions affect the direction of accretion flows, the formation of filamentary gas structures, and the propagation of shock fronts, producing observable asymmetries in X-ray surface brightness and jet morphology. Minor mergers within falling galaxy groups perturb the halo locally, creating transient distortions in the gravitational potential that ripple through the intracluster medium, enhancing turbulence and redistributing metals from supernova ejecta. Gravitational lensing also allows the measurement of halo ellipticity and substructure, revealing a triaxial shape with axis ratios of approximately 1.3 to 1. This elongation aligns closely with the distribution of X-ray cavities and radio jets, indicating that the dark matter potential guides the path of energy injection from the central black hole. The alignment is further supported by observations of molecular filaments with ALMA, which tend to follow the major axis of the halo, channeling cold gas toward the core along directions dictated by the gravitational field. Strong lensing arcs indicate that the gravitational potential well in the central 100 kiloparsecs is not smooth, but instead contains multiple peaks corresponding to massive subhalos, confirming that dark matter substructure significantly impacts baryonic processes. Simulations incorporating both baryonic and dark matter components show the influence of dark matter on feedback processes. Models indicate that halo mass concentrations amplify the effects of black hole-driven shocks and cavities, enhancing X-ray emission and prolonging the survival of cold filaments. Without the gravitational dominance of the halo, energy from jets and outflows would more easily escape the cluster core, potentially reducing star formation efficiency and lowering accretion rates. Substructure within the dark matter halo also affects the evolution of cluster galaxies. Infalling galaxies experience enhanced tidal forces and ram pressure stripping due to localized increases in gravitational acceleration, accelerating the removal of gas from their disks. Observations with Hubble and VLT show stripped tails extending up to 150 kiloparsecs, composed of both ionized and neutral gas. This stripped material contributes to the central accretion reservoir, while simultaneously enriching the intracluster medium with metals. Detailed ALMA mapping of these filaments indicates that many remain gravitationally bound to the cluster, spiraling slowly toward the core along dark matter-defined channels. The distribution of these stripped streams aligns closely with the dark matter subhalos, indicating that the gravitational landscape directly shapes the flow of baryonic material, impacting star formation, accretion rates, and the overall evolution of the central galaxy. Comparisons with other massive clusters show differences in Phoenix A's halo, while clusters such as Abell 1689 and Max J 717, 5 plus 3745 also host massive halos. Phoenix A has higher central concentration, richer substructure, and closer alignment with baryonic features. Lensing-derived mass maps indicate that density peaks in Phoenix A exceed 10 to the power of 14 solar masses within radii of 50 kiloparsecs, more compact than expected for clusters of comparable total mass. This central density affects gravitational confinement of gas, the formation of dense molecular filaments, and the ability of the central black hole to maintain near maximal accretion rates. compactness may also influence the formation of shock fronts, as supersonic motions encounter a steeper gravitational gradient, affecting turbulence and heating in the core. Numerical simulations show that potential wells associated with subhalos focus the propagation of shocks, producing regions of enhanced compression and heating. Observed X-ray brightness maps reveal filamentary enhancements aligned with these subhalo-driven channels, confirming the predictions of simulations. Gravitationally confined regions retain high metallicity and density over extended periods, allowing star formation and gas accretion to continue even in the presence of heating from shocks and jets. Observations indicate that these effects have persisted over the last 200–300 million years. Finally, the dark matter halo maintains gravitational binding in Phoenix A. By anchoring the cluster's mass and maintaining a deep gravitational potential, gas, stars, and galaxies remain bound despite repeated outbursts from the central black hole and ongoing mergers. The combination of the halo's gravitational structure with X-ray luminous plasma, relativistic jets, shock fronts, and molecular filaments influences the cluster environment. Rapid cluster growth. Phoenix A is not a static monument in space. It is a cluster in motion, rapidly accumulating mass and evolving dynamically on timescales that challenge conventional cosmological models. Observational evidence from deep optical and X-ray surveys demonstrates that the cluster's growth rate is among the highest measured in the local universe. Spectroscopic redshift measurements of over 300 member galaxies using Keck Observatory and the Gemini multi-object spectrograph indicate a velocity dispersion of 1,300 to 1,450 kilometers per second, reflecting both the gravitational depth of the dark matter halo and the influence of recent mergers. Such high velocities suggest ongoing infall of galaxy groups and subclusters, contributing to both the overall mass and the internal dynamical complexity of Phoenix A. Deep Chandra observations reveal multiple infalling groups within 1.5 megaparsecs of the core, each containing tens of galaxies with masses between 10 to the power of 12 and 10 to the power of 13 solar masses. These groups are moving at relative velocities of 900 to 1,200 kilometers per second, creating bow shocks and localized enhancements in X-ray emission. In some cases, the shocks extend over 200 kiloparsecs, compressing hot gas and triggering bursts of star formation in gas-rich galaxies. Observations with ALMA confirm that molecular gas in these infalling systems often survives initial RAM pressure stripping, feeding both localized starbursts and the central galaxy. Multiple, simultaneous infall events contribute to the high luminosities and star formation rates observed in Phoenix A compared with more relaxed clusters of similar mass. Hubble imaging of the central 500 kiloparsecs shows elongated stellar tails and filamentary gas structures extending up to 150 kiloparsecs from infalling galaxies. Spectroscopic analysis reveals that these streams are enriched in metals, indicating that supernovae within member galaxies have seeded the intracluster medium. The spatial alignment of these features with subhalos in the dark matter halo suggests that the gravitational potential channels stripped material toward the cluster core, where it can contribute to accretion flows and fuel further star formation. Mergers and accretion events influence the thermal state of the intracluster medium. X-ray temperature maps derived from Chandra and XMM-Newton data show regions exceeding 15 keV in localized shock-heated areas, particularly where infalling groups interact with the cluster core. These temperatures are higher than typical for clusters of comparable mass, reflecting the additional kinetic energy supplied by rapid accretion. Simulations suggest that such infall-driven heating can persist for several 100 million years, maintaining high-pressure gradients that drive turbulence and amplify the effects of black hole-driven jets and shock fronts. Strong lensing arcs in the central 200 kiloparsecs indicate that mass is being added preferentially along the major axis of the cluster, aligning with the distribution of infalling subgroups. Weak lensing measurements across 2 megaparsecs reveal filamentary structures connecting Phoenix A to surrounding galaxy overdensities, consistent with the predictions of large-scale structure formation. These filaments guide galaxy and gas infall, supporting continued cluster growth. Observed mass accretion rates are estimated at 200 to 300 solar masses per year, a figure confirmed by both lensing and dynamical modeling. Subclusters containing up to 50 galaxies each are observed merging with the main core at velocities near 1,000 kilometers per second. The interactions generate strong tidal forces, strip gas from satellite galaxies, and induce asymmetric X-ray brightness patterns. Observations show that these mergers can compress the intracluster medium along specific axes, enhancing cooling in some regions while maintaining high temperatures in others. ALMA data reveal that molecular gas streams from these events often reach the central galaxy within tens of millions of years, contributing to star formation and feeding the central black hole. Rapid cluster growth also has significant implications for dark matter distribution. N-body simulations, calibrated with lensing data, show that continuous accretion and minor mergers induce fluctuations in the central potential, temporarily enhancing the density of subhalos and deepening the overall halo. These fluctuations increase the gravitational confinement of hot plasma, stabilizing dense filaments and maintaining extreme conditions for star formation and black hole accretion. Observations indicate that the central 500 kiloparsecs of Phoenix A contain at least 15 significant subhalos, each with masses exceeding 5 times 10 to the power of 12 solar masses. Their spatial distribution and dynamical behavior are consistent with a cluster in an advanced stage of hierarchical assembly, undergoing repeated mass addition and structural reconfiguration. The cumulative impact of these growth processes is evident in the chemical composition of the intracluster medium. X-ray spectroscopy shows elevated abundances of iron, silicon, and sulfur, suggesting ongoing enrichment from both infalling galaxies and the central galaxy's supernova activity. The alignment of metal-rich regions with tidal streams and shock fronts indicates that the rapid assembly of the cluster directly contributes to the mixing of elements throughout the intracluster medium. Metallicity peaks in the core reach 2.5 times the solar value, with enriched filaments extending over 400 kiloparsecs, reflecting both the efficiency of gas stripping and the influence of the dark matter halo in guiding accretion flows. High-resolution X-ray imaging reveals an asymmetric surface brightness distribution and a pronounced temperature gradient along the northwest-southeast axis. Spectroscopic velocities of galaxies along this axis indicate a relative motion of approximately 1,200 km per second, consistent with a subcluster having merged within the last 500 million years. The energy deposited by this merger has generated additional shock fronts, amplified turbulence, and temporarily increased the efficiency of gas accretion onto the central galaxy. Finally, the deep dark matter potential attracts more galaxies and subclusters, whose infall generates shocks and turbulence. Redistribution of gas and metals supports star formation and black hole activity. Observational campaigns indicate that these processes have been active for the last 1-2 billion years. Multi-wavelength monitoring programs continue to reveal new infalling groups, filaments of cold gas, and shock-induced star formation. Gas stripping from cluster galaxies. Phoenix A is not only a cluster of extraordinary mass and activity, it is also a cosmic laboratory where galaxies are being systematically stripped of their gas, leaving behind stellar skeletons while feeding the cluster's central reservoir. Observations with the Hubble Space Telescope and the Atacama Large Millimeter or Submillimeter Array have revealed that gas stripping in Phoenix A occurs at an unprecedented rate, driven primarily by ram pressure interactions with the hot intra-cluster medium and tidal forces from both the central galaxy and subcluster mergers. These processes transform galaxies in a few 100 million years, reshaping the population of cluster members while enriching the intra-cluster medium with metals and molecular gas. The mechanics of ram pressure stripping are extreme in Phoenix A. The intra-cluster medium, with temperatures reaching 15 keV and densities up to 0.1 particles per cubic centimeter near the core, generates enormous dynamic pressure on galaxies moving at velocities exceeding 1,200 kilometers per second. Observations of spiral galaxies within 500 kiloparsecs of the cluster center show truncated gas disks, asymmetric H-alpha emission, and long tails of stripped material extending over 100 kiloparsecs. ALMA imaging reveals that these tails contain dense molecular clouds with masses up to 10 to the power of 9 solar masses per tail, providing a substantial contribution to the central gas reservoir and sustaining star formation in the core. Tidal stripping complements the effects of ram pressure. As galaxies pass near the dense dark matter subhalos, or the central galaxy, gravitational interactions distort their stellar and gaseous disks. Detailed kinematic mapping with the Very Large Telescope indicates velocity gradients of up to 400 kilometers per second along stripped filaments, confirming that gas is being drawn out efficiently while stars remain largely intact. Some infalling galaxies exhibit tidal tails rich in neutral hydrogen, which eventually mixes with the intracluster medium and contributes to the extreme X-ray luminosity observed in the central regions. Observed cases include several late-type galaxies with stripped tails aligned toward the cluster core, suggesting that the dark matter halo channels material preferentially along its gravitational axis. Studies estimate that individual galaxies lose up to 90% of their cold gas within 200-300 million years of entering the cluster core. This depletion contrasts with clusters like Coma or Virgo, where similar processes take 500-700 million years. The efficiency in Phoenix A is due to the combination of a dense, hot intracluster medium, high galaxy velocities, and the gravitational influence of multiple subhalos creating steep potential gradients. Stripped gas contributes to both the X-ray emitting plasma and cold molecular filaments feeding the central galaxy and its supermassive black hole. Hubble imaging reveals jellyfish galaxies, systems with asymmetric disks and elongated gaseous tails within 300 kiloparsecs of the central galaxy. Spectroscopic analysis confirms that these tails are metal-enriched, containing elements such as oxygen, silicon, and iron, consistent with prior generations of star formation within the galaxies. The velocity dispersion within the tails, measured at 200 and 300 kilometers per second, indicates that gas is moving both along and away from the galaxy, mixing with the ambient intracluster medium. ALMA observations show dense knots within these tails, which may collapse to form new stars as the material streams toward the cluster center. Late-type galaxies entering the cluster undergo rapid quenching of star formation as cold gas is removed, while early-type galaxies show signs of molecular cloud compression along tidal interactions. Surveys of over 400 Phoenix A member galaxies indicate that approximately 35% of spirals exhibit evidence of recent gas stripping, with star formation quenched in outer disks but enhanced along stripped tails. Filaments of cold molecular gas, traced in CO emission with ALMA, extend up to 80 kiloparsecs into the cluster core, providing a continuous supply of material to feed both star formation and the accretion disk of the central supermassive black hole. Combined with inflow from minor mergers and cooling flows, this process supports high luminosity and near maximal accretion activity. The spatial correlation between stripped filaments, X-ray cavities, and radiojets indicates that gas stripping dynamics are associated with feedback processes, redistributing or heating the material. In clusters such as Abell 2744 or Max J 717, 5 plus 3745, ram pressure stripping and tidal interactions occur at slower rates and affect fewer galaxies simultaneously. In Phoenix A, the combination of high intracluster medium density, high galaxy velocities, and complex substructure results in nearly all galaxies entering the core experiencing significant stripping within a few 100 million years. Observational studies show that the most intense stripping occurs within the inner 500 kiloparsecs, where the gravitational potential is steepest and the plasma densest. X-ray spectroscopy shows ion abundances reaching 0.7, 0.9 times solar, with localized peaks along the paths of stripped filaments. Oxygen and silicon are also enhanced, reflecting recent star formation in the parent galaxies before stripping occurred. The redistribution of metals along these channels increases the cooling efficiency of intracluster gas in some regions, contributing to the formation of dense molecular filaments that eventually accrete onto the central galaxy. Finally, observations indicate that gas stripping may be episodic and enhanced during minor mergers. Infalling groups with their own intragroup medium can increase local pressure and turbulence, accelerating the removal of gas from member galaxies. ALMA and Hubble data show examples of interacting galaxy pairs where stripped tails are more extensive than in isolated systems, extending up to 200 kiloparsecs and containing molecular masses exceeding 10 to the power of 9 solar masses. Ram pressure stripping, tidal forces, and merger-driven interactions remove gas from galaxies on timescales of a few 100 million years, funneling it toward the cluster core and sustaining both star formation and black hole accretion. High-rate supernova activity. Within the violent environment of Phoenix A, the rapid assembly of galaxies and the extraordinary star formation in the central regions have led to an equally extraordinary rate of supernova explosions. These stellar cataclysms occur far more frequently than in typical clusters, and their combined effect profoundly shapes the intracluster medium, enriches it with heavy elements, and fuels a dynamic feedback loop that interacts with both the central supermassive black hole and the surrounding gas. Observations from the Chandra X-ray Observatory, the Hubble Space Telescope, and the Very Large Telescope reveal that the frequency, energy output, and spatial distribution of these supernovae are unparalleled in any known cluster. Supernova surveys of the Phoenix, a central galaxy, indicate a rate exceeding 2 per year, inferred from both direct optical transient observations and X-ray measurements of shock-heated plasma. The explosions occur predominantly in the dense star-forming filaments and molecular clouds that dominate the central 100 kiloparsecs. ALMA observations show that the most active regions contain molecular masses of 10 to the power of 9 to 10 to the power of 10 solar masses, providing fuel for massive stars that end their lives as Type II supernovae. Rapid star formation, high gas density, and a continuous inflow of stripped material from other cluster galaxies sustain this supernova activity over timescales of hundreds of millions of years. High-resolution monitoring over a 5-year period, with Hubble identified more than 10 young supernova remnants within 200 kiloparsecs of the cluster center, indicating a continuous explosion frequency. In some cases, remnants overlap, producing turbulence and heating. Spectroscopy of these remnants shows shock velocities exceeding 10,000 kilometers per second, and electron densities in the shocked plasma reach 100 particles per cubic centimeter. High-resolution monitoring over a 5-year period, with Hubble identified more than 10 young supernova remnants within 200 kiloparsecs of the cluster center, indicating a continuous explosion frequency. In some cases, remnants overlap, producing turbulence and heating. Spectroscopy of these remnants shows shock velocities exceeding 10,000 kilometers per second, and electron densities in the shocked plasma reach 100 particles per cubic centimeter. Spatially resolved X-ray spectroscopy indicates that enriched gas extends along molecular filaments and stripped gas tails from infalling galaxies, not confined to the central galaxy. These metals enhance radiative cooling in localized regions, allowing some gas to condense into new star-forming clouds. Observations with the Hubble Space Telescope reveal clusters of young, massive stars forming along these enriched filaments. Long-term optical monitoring shows that Type Ia supernovae occur at a rate of approximately 0.5 per year, largely originating from older stellar populations in elliptical galaxies within the cluster core. The ion yields from these events further enrich the intracluster medium. The combination of Type II and Type Ia supernovae produces a chemical pattern with enhanced alpha elements in star-forming regions and ion enrichment more concentrated in older populations. Observations with the Chandra X-ray Observatory reveal cavities and bubbles in the hot gas coinciding with regions of supernova activity, in addition to cavities produced by the central black hole. These features show that energy from supernovae contributes to gas heating, turbulence, and the formation of low-density channels, which allow energy from AGN jets to propagate. Detailed mapping of velocity fields in the hot gas shows motions exceeding 300 km per second, consistent with the combined effects of supernova-driven outflows and merger-induced turbulence. Dense clouds within stripped tails and central filaments persist, as evidenced by ALMA observations of CO emission. The cooling times of these clouds, combined with gravitational confinement provided by the central dark matter halo, allow them to endure repeated shocks, supporting ongoing star formation and accretion onto the central black hole. In several filaments, the gas mass exceeds 10 to the power of 9 solar masses, sufficient to sustain both supernova activity and black hole feeding for tens of millions of years. High-resolution Chandra imaging reveals supernova remnants with radii up to 50 parsecs in the densest filaments, exhibiting shock velocities exceeding 10,000 kilometers per second. These remnants contribute to localized X-ray emission, enhance turbulence, and seed the surrounding medium with metals. Spectral line diagnostics indicate overabundances of elements such as neon, magnesium, and sulfur. The proximity of these remnants to molecular filaments suggests that supernovae can trigger compression in nearby clouds, promoting subsequent star formation episodes. Observations of 3 large infalling spirals show ongoing Type II supernovae in their trailing filaments, extending 150-200 kiloparsecs toward the cluster core. These events produce compact X-ray bright knots, which contribute to local turbulence and the enrichment of the intracluster medium. ALMA data confirms that these knots contain dense molecular gas capable of forming stars. In clusters with massive central galaxies, such as Abell 1835 and max J1149 supernova rates in the central regions are only a fraction of those observed in Phoenix A. The high activity in Phoenix A results from the combination of high star formation rates, rapid accretion of gas from infalling galaxies, and confinement of gas by the gravitational potential of the dark matter halo. Supernova explosions, AGN jets, and gas inflows interact in the cluster core. Metals ejected by supernovae are mixed with intracluster plasma through turbulence and shock fronts, forming a chemically heterogeneous environment. Observed metallicity gradients indicate peak values of iron in the core, exceeding 0.9 times solar, while oxygen and silicon are enhanced along infalling filamentary streams. Rapid supernova activity, combined with gas stripping from other galaxies, redistributes heavy elements throughout the cluster on relatively short timescales. Supernova-driven turbulence helps channel molecular gas into dense filaments, enhancing the inflow of material to the black hole while injecting energy into the intracluster medium. Multi-wavelength monitoring programs continue to observe transient events, including supernova explosions, X-ray flares, and shock fronts, compressed physical timescales. Phoenix A is not just a violent environment in terms of energy output. It is also a laboratory where cosmic processes unfold at an accelerated pace. Observations of the central galaxy and its surroundings reveal that the timescales for star formation, gas cooling, accretion onto the supermassive black hole, and chemical enrichment are compressed by factors of 2 to 5 compared to calmer clusters. This compression transforms the cluster into an evolutionary fast forward, where galaxies age, stars form and die, and gas cycles occur over hundreds of millions of years rather than billions. ALMA and Hubble imaging show molecular gas filaments with densities exceeding 10 to the power of 4 particles per cubic centimeter and masses of 10 to the power of 9 to 10 to the power of 10 solar masses. Under these conditions, massive stars form within 2.5 million years, a fraction of the typical timescale in quiescent spiral galaxies. Spectroscopic observations of these young stars reveal that the initial mass function is skewed toward higher mass stars, which evolve quickly and die as Type II supernovae. The combined star formation rate in the central 50 kiloparsecs exceeds 500 solar masses per year. X-ray observations from Chandra and XMM-Newton reveal that dense gas in the central 100 kiloparsecs cools at rates approaching 2,300 solar masses per year. Spectral line diagnostics show gas temperatures dropping from 15 keV near the outskirts to 3-4 keV in the central filaments over spatial scales of 5,100 kiloparsecs. These temperature gradients indicate that gas condensation and inflow toward the central galaxy occur on timescales of tens of millions of years. Observations of broad line regions in the core, combined with radio and X-ray measurements, suggest mass inflow rates approaching 800 solar masses per year. This inflow produces luminosities exceeding 10 to the power of 46 erg per second and powers relativistic jets that extend tens of kiloparsecs. Variability studies reveal that episodic feeding events occur on timescales of a few million years. Observations of X-ray line ratios show that the central intracluster medium reaches iron abundances of 0.9 solar, oxygen enhancements of 1.2 solar, and silicon enhancements of 1.1 solar within 300-400 million years. High-rate supernovae, efficient mixing due to turbulence, and the continuous infall of gas-rich galaxies contribute to these abundances. Observations of galaxy velocities with the Very Large Telescope show that infalling spirals and ellipticals move at velocities exceeding 1,200 kilometers per second relative to the cluster center. These high speeds increase the efficiency of ram pressure stripping, tidal interactions, and gas inflow. In some cases, entire infalling groups are stripped and absorbed within 200-300 million years. Chandra and XMM-Newton imaging reveal multiple shock fronts, with Mach numbers between 1.5 and 3, extending over tens of kiloparsecs. The shocks, driven by both supernova activity and AGN jets, heat the surrounding plasma, redistribute metals, and compress molecular gas filaments. The propagation of these shocks occurs over tens of millions of years. The shocks also interact with cavities produced by AGN jets, creating patterns of turbulence and density fluctuations. Filaments of molecular gas stripped from infalling galaxies, traced by CO and H-alpha emission, show star formation and supernova feedback along their entire length. The tails of these galaxies, often exceeding 150 kiloparsecs, are star-forming regions that feed both the intracluster medium and the central galaxy. The timescale for star formation in these tails is estimated at 20-50 million years. Dense filaments collapse, forming massive stars that die within a few million years, injecting energy and metals into the surrounding gas. This energy drives turbulence and shocks, which compress remaining gas and facilitate further star formation. The central black hole accretes material at high rates, producing jets that heat and channel gas toward the core. Cosmological hydrodynamic models, incorporating measured gas densities, dark matter profiles, and observed inflow rates, reproduce the evolution of the cluster. These simulations show that star formation in the central filaments can cycle through 3 to 4 generations of massive stars, while the central supermassive black hole can double its mass on a comparable timescale. Spiral galaxies entering the cluster core undergo quenching of their star-forming disks within 200-300 million years. Infalling ellipticals experience star formation episodes in gas-rich filaments, forming new stars in bursts lasting tens of millions of years. Observations show post-starburst features in several central galaxies, including strong ALMA absorption lines indicative of recent star formation followed by quenching. Multi-wavelength monitoring over the next decade will capture cycles of star formation, supernova explosions, and AGN activity. These observations can refine models of cluster formation, galaxy evolution, and black hole growth. Ongoing observation of Phoenix A. Phoenix A remains the most violently active galaxy cluster known, and understanding its rapid evolution requires continuous observation across multiple wavelengths and timescales. Astronomers around the world have coordinated extensive monitoring programs using space and ground-based facilities to capture the cluster's fast-paced activity. Instruments such as the Hubble Space Telescope, Chandra X-ray Observatory, XMM-Newton, ALMA, the Very Large Telescope, and the Atacama Pathfinder Experiment play complementary roles, allowing researchers to track star formation, supernova explosions, gas dynamics, black hole activity, and chemical enrichment in real time. Optical monitoring focuses on transient events, particularly supernovae, starburst regions, and variability in the central galaxy. Long-term observations with Hubble and the Subaru telescope have revealed supernova explosions in both the central galaxy and stripped filaments of infalling galaxies at rates exceeding 2 per year. These surveys employ repeated imaging of the central 200 kiloparsecs at intervals of weeks to months, capturing the evolution of young stellar populations, shock fronts, and light curves of individual explosions. Optical data provides information about the metallicity and age distribution of stars in the filaments. Chandra's high-resolution imaging reveals shock fronts, cavities, and temperature variations, while XMM-Newton's large collecting area allows precise spectral measurements of ionized gas. Observations show temperatures in the central 50 kiloparsecs, reaching 12 keV, while X-ray luminosities approach 10 to the power of 45 erg per second. These measurements track cooling rates, turbulence, and energy injection from both AGN jets and high-rate supernovae. Continuous X-ray monitoring allows observation of episodic events, such as outbursts from the central supermassive black hole as they propagate through the surrounding gas in tens of millions of years. The Very Large Array and ALMA detect jets extending tens of kiloparsecs from the central black hole, with energy outputs exceeding 10 to the power of 46 erg per second. Radio mapping reveals interactions between jets and dense molecular filaments, where turbulence is generated and gas is compressed to form new stars. ALMA detects molecular transitions such as CO, allowing tracking of gas inflow, filament survival, and accretion onto the central black hole. Infrared observations from the Spitzer Space Telescope and the James Webb Space Telescope penetrate dusty star-forming regions in the central galaxy and along filaments, revealing massive young stars embedded within dense molecular clouds. Photometric measurements indicate star formation rates of 500 to 700 solar masses per year in the central regions. Infrared data capture reprocessed radiation from supernova-heated dust, allowing estimation of energy injection and metal production in obscured regions. Spectroscopic surveys complement imaging by providing velocity and chemical information. The Very Large Telescope and Keck Observatory measure redshifts, line widths, and elemental abundances across hundreds of galaxies in Phoenix A. Observations show galaxy velocities exceeding 1,200 km per second in infalling groups, and turbulence in the intracluster medium with speeds of 300-500 km per second. Metallicity measurements indicate iron abundances of 0.9 solar, oxygen enhancements of 1.2 solar, and silicon enhancements of 1.1 solar in the core, while filaments from stripped galaxies show similar enrichment patterns. Simultaneous observations across optical, X-ray, infrared, and radio bands allow correlation of star formation bursts with supernova explosions, molecular gas inflows, and AGN feedback. Time-resolved imaging shows massive star formation episodes in central filaments occur over 5 million years, immediately followed by high-energy supernova events that trigger shocks and turbulence. Gas inflows feeding the supermassive black hole proceed in parallel with episodic accretion events on similar timescales. Citizen science programs have contributed to monitoring Phoenix A. Projects like Galaxy Zoo have enabled volunteers to identify transient features, including filamentary star-forming regions and candidate supernovae, providing data that complements professional observations. These contributions increase the cadence of observations and allow identification of unusual events for follow-up using large telescopes. Despite extensive monitoring, challenges remain. The distance of Phoenix A, roughly 5.7 billion light-years, limits spatial resolution achievable with current instruments, making it difficult to resolve individual massive stars or the smallest molecular clouds. Observational biases affect supernova detection, as explosions in dense filaments can be obscured by dust. X-ray spectroscopy is limited by sensitivity, so smaller-scale turbulence or faint cavities may go undetected. Researchers address these challenges by combining multi-wavelength data and using modeling to infer sub-resolution structures. Ongoing observation strategies include high-cadence imaging, long-term spectral monitoring, and coordinated campaigns across multiple observatories. Campaigns integrating Chandra, ALMA, and Hubble imaging over months have captured the sequence from star formation to supernova explosion to shock propagation within individual filaments. Planned future observations with the Extremely Large Telescope and Atacama X-ray Observatory will refine measurements of gas kinematics, metallicity gradients, and black hole accretion rates. Simulations incorporating measured gas densities, black hole activity, star formation rates, and supernova frequency suggest that central regions may undergo 3 to 4 rapid cycles of star formation and feedback. Observational campaigns aim to verify these predictions by tracking filament evolution, supernova remnants, and AGN jet propagation. Finally, ongoing observation of Phoenix A has broader implications for astrophysics. By capturing accelerated evolution in action, scientists gain insight into feedback mechanisms, chemical enrichment, star formation physics, and black hole growth under extreme conditions. Phoenix A serves as a cosmic laboratory, offering a live demonstration of processes that typically unfold over billions of years, compressed into hundreds of millions. The cluster exemplifies how extreme environments can drive rapid evolution, providing crucial benchmarks for theoretical models of galaxy and cluster formation throughout the universe. Phoenix A continues to surprise astronomers with its complexity and intensity. Every new observation reveals additional layers of violent activity, from high-velocity shocks in the intracluster medium to rapid cycles of star formation and supernova explosions. By maintaining continuous monitoring programs across multiple wavelengths, scientists ensure that the dynamic behavior of this extraordinary cluster is captured in real time, allowing the most detailed examination ever achieved of one of the universe's most extreme environments.